Good day, class. Today we're going to pick up with where we left off from day one. We left off doing some practice problems. So here, of course, we have the function, the absolute value function, which, of course, looks like a v. So we have it, and of course, it looks something like this. All right, so if they want us to write it as a piecewise function, remember a piecewise function is just a function that is written in several pieces. Usually has this funky looking bracket. All right, so again, if we kind of think of that absolute value function, all right, looking like a V, we can kind of break it up into two different pieces. We can break it up right here at the origin. So this will be one piece, this will be another piece. Of course, they're both lines, so we're going to be writing them in y equals mx plus b. What is going on? So of course we need the slope and we need the y-intercept. If we think of this piece here, if we think of the absolute value function x, right? Of course, if we plug in 0, we get the point 0, 0. If we plug in -1, we get the point -1, 1. If you plug in -2, you get the point -2, 2, and so on, right? So my y-intercept, of course, is 0, right? My slope, we're going down here, so it's a negative slope. Right? If we think of it as rise over run, I go down 1 and over 1. So my slope is -1. My y-intercept is 0. Of course, we don't have to write this as y equals -1x plus 0, right? We can really just write it as -x. So in my piecewise function, y equals -x, but then we have to put the condition on it, right? Over what x values is this true? Right? Well, obviously from 0 all the way as far left as we want to go, so negative infinity. So really what we can just say that this graph is the same graph as y equals -x for all x's less than 0. All right, we can do the same thing over here. Of course, here we would have the point 1, 1. We would have the point 2, 2. All right, so now it's very similar, except now we're going up, so our slope is +1. All right, so there for this piece we would have y equals 1x plus 0, because again my y-intercept is 0. My slope is 1. All right, we're going up 1 over 1. All right, so again, we don't have to write it like this. We can just say that this is just x. All right, so we come over here and we say, okay, well, the graph of the absolute value function is equal to just x. All right, but now this is true for all of my x's greater than 0. Of course, we're actually leaving out the point 0, 0 here, which is easily rectified by taking either one of these. It doesn't matter which one, since both of them hit the point 0, 0, and just making one of them or equal to. Right, so now we move on to a more commonplace piecewise function. Right, but all it wants us to do here is evaluate the piecewise function. So we're not graphing yet, we're not doing any of that stuff. All we have to do is evaluate. So first we want to find f of -4. Right, well, in order to do that, we need to determine which one of these we're going to plug it into. Right, in order to do that, we check our conditions over here. Okay, so we plug the x that we're looking at, in this case -4. We plug it in for x in my first condition here, and I say, okay, is negative 4 less than or equal to negative 2? That answer is yes, negative 4 is less than negative 2, which means I plug it into this top piece. So I say 3 times negative 4 plus 1, that's negative 12 plus 1, which is negative 11. All right, now we move on to f of negative 2. I do the same thing. Okay, which one of these pieces, right, am I really going to be plugging this into? All right, so we check our conditions again, plug negative 2 in here. Is negative 2 less than or equal to negative 2? The answer is yes, because it's equal to. So again, I'm plugging it into this top piece. So I say, all right, 3 times negative 2 plus 1, that's negative 6 plus 1, which is negative 5. And finally, I look at f4 here. We say, okay. I check my conditions again. I plug it in here. Is 4 less than or equal to negative 2? No, it is not. So I come down here, plug it in here. Is 4 greater than negative 2? Yes, it is. So that means I want to plug it into this second piece right here. So I say, okay, negative 2 times 4 plus 3, that's negative 8 plus 3, which again is negative 5. And that's it. When it comes to evaluating piecewise functions, that's all we have to do. Right, so again, same thing. If you're watching this video, I would go ahead and pause it right now, try these out on your own, then hit play to check yourself. Right, so again, if we're looking at f of 0, right, we go ahead and check our conditions. Is 0 less than 3? Yes, it is. So I plug it into this first piece, and 0 squared, of course, is still 0. So f of 0 is 0. I move on to f of 3. Again, check my conditions. Is 3 less than 3? No, it is not. Go to my next one. Is 3 equal to 3? Yes, it is. So I'm plugging 3 into this second piece here. So we have 2 times 3 plus 3, that's 6 plus 3, which is 9. Next I go to f of 7. Again, check my conditions. Is 7 less than 3? No, it is not. Is 7 equal to 3? No, it is not. Is 7 greater than 3? Yes, it is. So I'm going to be using my third piece here. I plug 7 in there. 7 minus 4 is equal to 3. I don't feel that we need to do another one of those. All right, given f of x is equal to 3x plus 2, find all values of x such that f of x is equal to 0. All right, now, what I would do here is pause this video and do it. All right, just try this without any instruction. It's pretty straightforward from Algebra 1 and Algebra 2, but a lot of students make a very common mistake here. So go ahead and hit pause and try it yourself and see if you make this very common mistake. Right? It's not a problem if you do, we just want to catch it early and correct it. All right, so right here, this says that f of x is equal to x, right? Now, a very, very common mistake that students make is they plug 0 in for x. Okay, we need to understand that this is not the same thing as f of 0. Right, f of 0 means that you're plugging 0 in for x. F of x equals 0, if you remember when you first learned function notation, f of x took the place of y. So this is actually saying y is equal to 0, where this is saying x is equal to 0. And those are very different things. Right? Another very important thing to know in mathematics is when two things are equal to each other, they are interchangeable. Right? So wherever you see one, you're able to replace it with the other. So if I'm starting off with f of x equal to 3x plus 2, right, I can replace this entire f of x with 0 because they are equal to each other. So of course now I simply subtract 2 from both sides, then divide by 3, and you get x is equal to negative 2/3. Right? So if you got 2 here, that means that you made the very common mistake of plugging 0 in for x. All right, so we have the same type of thing here. Again, if you're watching this video, I would hit pause here, try this yourself, and then check it. All right, so again, like we said before, whenever two things are equal, they are interchangeable. So where I see f of x here, I'm allowed to replace it with 0. So we have 0 is equal to 5 minus 2x over 3. First step I want to do here is multiply both sides by 3. All right, so what is 3 times 0? When you're asked that out loud, it's quite obvious that it's 0, right? But you'd be surprised how many people say that this is 3, right? Not that they don't know that 3 times 0 is 0, right? But it's just, they do it quickly and they don't really think, and they put 3 here. So please do not make that mistake. So from here, of course, we just add 2x to both sides, divide both sides by 2, and x is equal to 5/2. Right? Now we're wanting to find the domain of each of these functions without a calculator. Right? Remember that the domain is all of the possible x values, right, that a function can have. Right? From a graph, you just see what all x values does it touch from left to right. All right? You can also think of it as what things are we allowed to plug in for x, right? Well, in this first problem here, right, it's just a regular linear function. So when we're talking about real numbers, there's nothing that we're not allowed to plug in here. I can multiply absolutely any number by 3, and then I can add 2 to that product, right, no matter what number I plug in. So my domain here is all real numbers, right? There's a few ways that you can write it. You can write it negative infinity to infinity. That's called interval notation, right? You could also write it using set builder notation, which says, okay, all x's such that, all x's is such that x is between negative infinity and infinity. You could do that. You could also just say my domain is all real numbers. Any of those would work. All right. The second one here, x squared minus 2x plus 3, that's a quadratic function. Right? But again, when we're talking about real numbers, there's nothing that's going to stop us from plugging any real numbers in here. I can take any real number and I can square it. Right? I can multiply any real number by -2, and then I can combine these, and I can add 3 to that. No problem whatsoever. So this is also all real numbers. You can pick any one of these 3. I really don't care. All right. Looking at this next function, f of x is equal to the square root of x plus 3. All right. Well, are there any x's that we're not allowed to plug in here? All right. A lot of x's will work. All right. But what if I wanted to plug in, I don't know, -5? So -5 plus 3 is -2. The square root of -2 is, oh wait, we can't do the square root of a negative number. All right. So what we really need to worry about, so up here it's very easy, right? Okay, well, we just can't plug in any negative numbers. So that means that my domain would go from 0 to infinity, including 0, because I am allowed to take the square root of 0. So do be mindful that in interval notation, the bracket means that we actually include that number that we're allowed to use it, right? I'm not going to write all of these for every one of these problems. I primarily use interval notation. If you use another notation, I don't really care, but from here on, I'm just going to use interval notation for consistency. Okay, so what numbers can I not plug in here? All right, well, the main thing is that we can't have negative numbers. Well, how can I guarantee that I don't have any negative numbers under this square root? Well, all I have to do is take what's under my square root, in this case x plus 3, and I say, okay, well, that has to be greater than or equal to 0. If you're greater than or equal to 0, you are not negative. All right, so then I can solve this like a regular inequality. All right, I can subtract 3 from both sides. X is greater than or equal to negative 3. All right, so using my interval notation, I would say, okay, well, I can go from negative 3, including negative 3, because it is or equal to infinity. All right, so that's all values negative 3 or greater. We can do the same thing here. All right, I say, okay, I have 5 minus 2x. Again, that's under a square root, so I can just say that has to be greater than or equal to 0. Solve it like a normal inequality. So now I'll divide both sides by negative 2. We do have to be careful when we're dealing with inequalities. Whenever we multiply or divide by a negative number, we have to flip this inequality. So x is less than or equal to 5 halves. All right, so my domain, again, in interval notation, would be negative infinity to 5 halves, including 5 halves. This is all x's less than or equal to negative 5. All right, finally here, we don't have a square root, so we don't have to worry about, this being positive, right? Because we can divide by negative numbers, that's perfectly fine. However, there is one number that we're not allowed to divide by, right? Namely 0, all right? So whenever you have a rational looking function, which means it looks like a fraction, and whenever you have a variable in the denominator, all you have to do is take whatever is in the denominator and say that thing cannot equal 0. So in this case, x cannot equal 0. All right, well, if we want to write that in interval notation, we say, okay, well, we can go all the way from negative infinity all the way to 0, but we can't include 0. That's why I have the parentheses. And then I have to union that with 0 to infinity, again, not including 0. So this basically says that I can go from negative infinity to infinity. I just can't use 0. All right, so similar stuff here. Again, I don't have a square root, but I do have a variable in the denominator. So I say, okay, 2x plus 3 cannot equal 0. So if I solve this, I subtract 3, divide by 2, x is equal to negative 3 halves. All right, same thing here. I say x squared minus 2x minus 3 cannot equal 0. This is a quadratic. We typically like to factor quadratics. Right, if you don't remember how to factor, you definitely need to brush up on that. You're going to need that a lot in this course. All right, so this will factor to x minus 3 and x plus 1. Of course, when you have multiple factors set equal to 0, you set each one equal to 0 and solve. So x minus 3 cannot be 0, and x plus 1 cannot be 0. So here we know that x cannot equal 3, and here x cannot equal negative 1. All right, so my domain here is going to be a little bit messy. It's going to go from negative infinity to negative 1, not including negative 1. All right, from negative 1 to 3, not including either of those, and from 3 to infinity. All right, so again, this is saying, okay, I go from negative infinity to infinity. I can't include negative 1, and I can't include 3. All right, when you do write your domain in interval notation, do make sure that you write it in the order of a number line, right? Negative infinity is furthest to the left, negative 1 comes next, 3 comes further to the right of that, and infinity is furthest to the right. Don't mix these up, don't put them out of order, all right? Make sure that you're doing it correctly. All right, here we're combining these two things. I say, okay, I know that I can't have any negatives under square roots, so I say x plus 5 has to be greater than or equal to 0, so x has to be greater than or equal to negative 5. I know that we can't have zeros in denominators, so x minus 6 cannot equal 0, so x cannot equal 6. All right, I want to combine both of these things into a domain, so I know that I can start at negative 5 and include it, Right? This would say that I could go all the way to infinity, but this says I can't use 6. So I go to 6, I don't include it, I union it with 6 all the way to infinity. So this says I can go from -5 to infinity, including -5, but I'm not allowed to include 6. All right, finding domain and range with a calculator. All right, I'll just go ahead and look at this one first. All right, so if I do that, all we have to do is go to y equals. I can plug this thing into my calculator. So 16 minus, you do have to use this variable button for your x. All right, squared. We graph that thing. Okay, so it looks just like a little semicircle. You can actually zoom square this thing if we want to make it look nice and prettier. All right. Now it looks like it doesn't quite go down and touch the x-axis, but it actually does if you want to test those kind of endpoints, if you will. This is -4, this is +4. So if I plug -4 in for x, -4 squared is 16. 16 minus 16 is 0. We are allowed to take the square root of 0, so that's perfectly fine. Same thing would happen with +4. So my domain here, all right, is going to be -4 to 4. It also wants us to find the range. The range, of course, are the y values. Well, we know that it goes to 0 because we plugged in our -4 and 4 and got 0. All right, and it goes all the way up to +4. All right, so what we're going to do here is say from 0 to 4. Finding domain and range from a graph, like actually looking at a picture, isn't terribly hard at all. So I'm not going to spend a whole lot more time on those. If you need some extra help, just let me know. I'm more than happy to help you. We'll skip this stuff for the time being. All right, this is really the last major thing that I want to get to. All right, this is called difference quotients. Although there are many different difference quotients, this is by far the most important one that you will ever see. This becomes very important in calculus. In fact, once we study limits here a couple of units from now, and we combine the idea of a limit with this very specific difference quotient, it will then become the definition of derivative, which will essentially be your entire second unit of calculus once you get there. And limits will actually be your first unit of calculus when you get there. All right, so let's go ahead and look at some examples. All right, first I'm going to go ahead and look at f of x equals 3x plus 2. All right, I'm using my difference quotient, f of x plus h minus f of x all over h. All right, so I'm going to need two things here. I'm going to need f of x plus h, and I'm going to need minus f of x. And of course, for now, I'm just using 3x plus 2 as my f of x. All right, so to find f of x plus h, for some reason, this confuses a lot of students, right? But if you were doing f of -2, you would just plug -2 in for x. If you were doing f of 5, you would just plug 5 in for x. Well, if you're finding f of x plus h, you literally plug x plus h in everywhere you see an x. So I rewrite my function, 3, but where I see an x, instead of putting x, I put x plus h. Just like you would plug in a 2 or plug in a 5, you plug in x plus h. Well, now we can go ahead and distribute this. So 3 times x is 3x, plus 3 times h is 3h, and then I still have my plus 2. That's it. That is my f of x plus h. To find minus f of x, all I do is take my entire f of x and distribute a negative to it. All right? So when I distribute that negative, I get minus 3x minus 2. Right? Well, remember, I said earlier that whenever two things are equal to each other, they are completely interchangeable. So since f of x plus h is equal to this, and minus f of x is equal to this, over here in my difference quotient, I can replace these things with these two things. Right? So instead of f of x plus h, I'm allowed to write 3x plus 3h plus 2. Instead of minus f of x, I'm allowed to replace it with minus 3x minus 2. And that's all still over h. All right, well, If we do this correctly, all right, then nice things should happen. So here I have a positive 3x and a minus 3x that cancel. Here I have a plus 2 and a minus 2 that cancel. All right, so now all I'm left with, all right, is 3h over h. Of course, now my h's will cancel, and my answer is just 3. That's it. We are done. All right, so now I'm going to go ahead and take this thing. Go to a new slide. All right, so now I'm going to do the second one of these. All right, so I'm only looking at this as being my f of x. All right, and I'm still working with my difference quotient. All right, f of x plus h minus f of x all over h. All right, so I'm still needing my same two pieces, so I need f of x plus h. All right, so again, wherever I see an x, I just plug in x plus h. This is squared. Minus 3, instead of x, I plug in x plus h, and then plus 2. A lot of students make the mistake here of saying that this is x squared plus h squared. We do have to be careful. X plus h squared is really equal to x plus h times x plus h. And when we distribute that, we actually end up getting x squared plus 2xh plus h squared. All right, so this is x squared plus 2xh plus h squared. Then I can distribute this negative 3, negative 3x minus 3h, and then I have plus 2. All right, and then of course I still need my minus f of x. So I just negate this entire thing, distribute a negative to all of it. So negative x squared plus 3x minus 2. All right, so now when I plug it into my difference quotient, f of x plus h minus f of x all over h. Remember, when things are equal to each other, they are interchangeable. So instead of f of x plus h, I can write x squared plus 2xh plus h squared minus 3x minus 3h plus 2. Instead of minus f of x, I can rewrite it as minus x squared plus 3x minus 2, and that's all over h. Again, if you did things correctly here, lots of things cancel. X squared minus x squared plus 3x minus 3x minus, I'm sorry, that should have been plus 2. Oh yeah, minus 2 plus 2. So those cancel. All right, so now we're just left with 2xh plus h squared minus 3h all over h. Notice everything up top has an h, which means I'm allowed to factor it out. Now I can cancel my h's, and this is my answer. All right, and your homework from everything that we covered today is already up on Delta Math.